talk very briefly about the difference between direct current and alternating current. Direct current is a constant flow of electric charge in one direction only, and we can abbreviate direct current as DC. Okay. DC current has a constant voltage source like a battery and a constant current. So here we have a graph that shows the potential or voltage in DC current and the current in the DC circuit as a function of time, and you see that they remain fixed over time. And this is exactly the same thing as creating a circuit that's being powered by a battery. That battery's voltage remains fixed, so the current remains fixed and it doesn't fluctuate in the circuit. And then we have alternating current. Alternating current is the flow of electric charge that periodically or alternatively reverses direction. So here's a plot of potential and current as a function of time if we have an AC alternating current source. AC has a voltage source and current that varies sinusoidally, like the electricity supplied to homes and businesses. So the electricity that's coming into our homes, the electricity in the power lines, that's all alternating current, where the voltage and the current fluctuate sinusoidally in time. We'll find out later that this is useful and important for us, especially when we think about magnetic fields. Alternating current has a frequency. The frequency in units of hertz, 1/2 of alternating current or voltage is the number of times per second that that voltage or current fluctuates from its maximum value, its peak value of V sub naught here. So in all these equations, V sub naught, that's the maximum potential that our alternating current can achieve. Here we have a plot showing the potential of a power source in an alternating current circuit. We have the maximum potential that we can achieve up here, V sub naught. And you see that it fluctuates like a sine or cosine pattern around some zero position. The equation that describes what we call the instantaneous voltage is right here. The instantaneous voltage, that's the voltage at any time, equals our maximum voltage that we can achieve times sine, and inside that sine argument, you have 2 pi frequency times time. So I could ask you to find the potential in an alternating current circuit at any time t if I tell you the frequency, if I tell you the maximum potential. And I can do the same thing for the current. And that was what we call the instantaneous voltage or current if we're finding that voltage or current using this equation at some particular time t. And since power is equal to current times voltage, I can multiply both of these equations together. So the power at any time t equals our maximum current times our maximum voltage times, this is essentially sine squared of 2 pi frequency time. So the argument of the sine is the 2 pi frequency times time. When you're typing all that into your calculator, you have sine, parentheses, you've got 2 pi times frequency times time, then you close the parentheses. Your calculator needs to be in radian mode. Here, we're not talking about anything with degrees. Here we're thinking about frequency and time. Inside our sine function, we want to use our calculator in radian mode when we're solving these sorts of problems. Now we remember that power is equal to current times voltage. So we saw an alternating current, we can have, actually, well, here's the graph. At some time t, both of my current and my voltage can be positive, and at some time t, both of my current and my voltage can be negative. These signals for current and voltage are in phase, which means that their troughs line up with their troughs and their peaks line up with their peaks, and they cross zero at the same point. So when we're in phase, and let's say we're down here we're trying to find the power, we're multiplying a negative current times a negative potential, which just means that that potential or current is flowing in the opposite direction from what it was before. Then those minus signs cancel. And actually, all the time, whenever you're finding power for this signal for current and potential, anytime you're finding power here, that power is going to be a positive value, because when we have our negatives times a negative, that gives us a positive. So over here then would be the power graph that we would get from this same curve for our current and potential. So our maximum power that we could achieve would be the maximum current times the maximum voltage, right? So the average current then, if we draw our graph right here, the average current is 1/2 times our maximum current times our maximum potential. And that would be right here. That's our average power. And we also, so that's our average power, and that's this quantity over here, 1/2 our maximum current times our maximum potential. But we also have something that we call our RMS, root mean squared current, and our RMS, root mean squared voltage, not velocity, this is voltage. So for alternating current circuits, we define an RMS, root mean squared current and voltage rather than an average, because, well, when we think about the current and the potential, they're fluctuating around some 0 point. So if you took the average of those, like literally, you would get 0. And so we do instead this RMS calculation to get the average of kind of stand in for like the average of the current and the potential. And so those RMS current and voltage is just the maximum current or voltage divided by the square root of 2. So our average power is equal to 1/2 times our maximum current times our maximum voltage in alternating current. Our average power in alternating current is equal to our RMS current times our RMS potential. And of that, we're taking IO over the square root of 2, the RMS current, times VO over the square root of 2. That's our RMS potential. Then we have I times V. And then if you take the square root of 2 times the square root of 2, the square root signs kind of cancel each other out, and then you get back just the 2. So if you take the square root of n times the square root of n, you just get back n. And then with our multiplying our RMS current times our RMS potential, we also get the same equation that we saw earlier for the average power. So we have all of these relationships for our alternating current circuits. We have the instantaneous voltage here, instantaneous current. We have our RMS current, our RMS voltage, and we have all of these different ways to calculate the average power. So we went through this one here. The average power is also the same as V squared over R, where that V is the RMS potential. It's also equal to I squared R, where that current is the RMS current. So with these relationships here, we're going to find the voltage between terminals of an AC voltage source. So here we have our equation for the voltage between the terminals of an AC voltage source. We've seen this already. In this equation, we're going to let our maximum voltage be 120 volts. That's our peak voltage here, this quantity. And we're going to take this quantity, 2 times pi times the frequency, to be 310 hertz. And I'm going to ask you, what is the instantaneous voltage of this power source at 4.3 seconds? To find that, you'll use this equation right here. You've got your peak voltage, 120 volts, goes right in here. Sine, be in radian mode. 2 pi f is going to be 310 hertz. And then you multiply that by our time at which we're evaluating this potential, which is 4.3 seconds. And then you'll find your instantaneous potential. And then I'd like for you to, at this instant, compare our instantaneous potential to the peak voltage and the RMS voltage. And we saw how you find the RMS voltage here, where V sub naught, that's our peak voltage. So I'd like for you to think about all those different types of voltages, the instantaneous, the RMS, and the peak voltage, and compare them. How do they compare in size? We're going to end our study of current here by talking about electrical shock hazards. This is important for us to understand, and it's directly related to our real life experience. The severity of an electrical shock delivered to humans depends on four things here. Depends on the amount of current that's running through your body, the path taken by the current, because the current wants to take the path of least resistance, which is going to mean it's going to travel through the part of your body that has the least electrical resistance, and then it's going to enter into the ground. It's going to try to pass through you and then through the Earth's ground. The severity of the electrical shock that you receive also depends on how long it lasts and the frequency of the current. We saw the frequency of the alternating current changes how fast that current fluctuates each second, changes direction each second. So if we think about the current here in milliamps, 1 milli is 10 to the minus 3 amperes. 1 milliamp of current running through our body is where we start to get uncomfortable with feeling that current running through us. 5 milliamperes is the maximum amount of current that we can receive to our bodies without having any damage to us. And then at 10 to 20 milliamperes, that's when we start to get contractions of our muscles. When you reach this amount of current running through you, that's when your muscles kind of like spasm. And like if you're touching a power line and you've got that amount of current running through you, your muscles are going to kind of contract, and that can actually, well, it could either kind of push you back and away from the wire as your body spasms, or it could actually cause you to like grab and hold on and not be able to let go of that wire because the contraction of your muscles. And it can also stop you breathing. We start experiencing pain at 50 milliamperes. In our houses, we have circuit breakers, maybe in the wall or like in your supply room or something, that limit excessive currents running to our homes. And so if something happens to the power grid and we get an increase of current through our homes, that current is running through the circuit breaker. And these little fuses in the circuit breaker are meant to break that current that's running through, to break the circuit, to break that circuit for the current that's running through our houses. So it can essentially shut off the current that enters into our house if we exceed some threshold level of current. So if you've got, like your hair dryer and a curling iron and the washing machine all working in the same room, and you overload your circuit, you can actually blow a fuse in your circuit breaker. And that's just the circuits in your house trying to protect you from harming the electrical power grid and getting too much current flowing through that room in your house. Fuses, there are fuses that are also in electrical devices. In the little voltmeters that we use in lab, there's a fuse in there that will break and cause the voltmeter to not be able to take any more measurements if you exceed a particular amount of current. And that protects the electronics inside the voltmeter from frying up if you supply it with too much current.